This conference will now be recorded.
Hi everyone, good morning. Hope you're able to see my screen as well as able to hear me clearly. Please confirm that.
Yes.
Yes, Madhu sir.
Okay, thank you so much. So welcome to the fourth session of our machine learning foundations course. So in this session, we will continue to talk about the most important concepts of machine learning, because these things will help us to smoothly do our projects. And as we do projects, uh, this kind of terminology, the concepts will actually give a lot of clarity on what we are doing, why you are doing when you are doing projects. So today we will spend an hour to understand the most important concept of machine learning. In fact, we refer to it as the heart of machine learning. So that is actually model complexity. So we'll talk about this in a little bit of detail. Again, we'll not go to a lot of depth uh, because our focus is to understand a lot of things broadly and also actually complete 2 to 3 good projects from start to finish, instead of wasting a lot of time going into a lot of depths which may not be useful at this moment. They will become useful later. So that is the overall approach we are taking. I want to keep on telling you that. And this approach we are deliberately taking. Intentionally, we are taking that approach because this is the best approach for the beginner level people. Okay. So today we'll talk about model complexity. So what we will do is that why it is important. I will take you through a case study which is again published in the Medium blog by University of Berkeley. Just I took that and put it for you, the case study around this model complexity. And then as we discuss this issue of model complexity, we will come across more terminology. Terminology like overfitting, underfitting, high bias, low variance algorithms, high variance, low bias algorithms. A lot of this kind of terminology will come across, and our goal for today is to, as clearly as possible, we will understand the terminology. That is the goal we are setting for yourself. Anybody who is not asking a question, please mute your mics. And again, as usual, every day I'm telling, interrupt me anytime to ask a question. That will make it the whole session more interesting. So let me actually have a blank screen now. I will write into the screen. Uh, Basically, before I take you through that case study of around this idea called model complexity, let us conduct a little bit of small experiment, because we'll be using some terminology. Still, some things may not be clear because practically we didn't do anything so far. We will do at that time. A lot of issues will be anyway clarified for you. So let me take, we are doing a very simple uh, exercise. Okay, let me choose my pen. Um, okay, I'm choosing my pen. And so let's say we are conducting an experiment. Here we will, we have a set of mouse. We are a biological research organization. So what we are trying to do is that we are having a set of 10-15 mouse with us. And then first thing is that we are weighing each mouse. So handwriting is not very good because I'm using stylus. I'm not comfortable writing on a screen, but please pardon me for that. So we will weigh each mouse, and then also we will measure the length of each mouse. Okay, so I have weight and length of mouse. So basically this is my input feature. Usually we refer to it as X in our machine learning terminology, and my target variable is length. I refer to typically as a capital Y. So weight is my input feature, length is my um, target variable. So target variable, typically we use that to predict something. So let's say I weighed first mouse and it is actually weighing, they don't weigh 2 grams, 20 grams, but to bring both weight and length into same scale, I'm calling 20 grams as 2. Okay. And then I measured its length. So it is some 3 centimeters. Then second mouse I have measured, it is 4 and 4. Then third mouse I measured 3 and 2. Then 5 and 6. Then 6 and 6. 7, 7 and 5. 7 and 6. So I weighed some 7 mouse out of the 15 that I had, and I calculated and put it in my table. First column is weight, the second column is length. It is not a big rocket science experiment, but we are doing that experiment so that I want to build a model, and using this data, I want to train my computer using some particular algorithms, and then I want to uh, actually ask the computer, I will give another mouse with 60 grams, and I will ask it what is the length, and maybe I will ask 5 and what is the length, and I will give 2 and what is the length, because rest of the 3 mouse I want to actually uh, ask the machine and let it predict. That is that is the experiment we are doing. Okay, so let's see how, looking at these numbers, we don't know any trend on our own, because really what we are doing by machine learning, we are teaching computers to learn any patterns that may exist in this data to be able to make some predictions or decisions. But whenever we see a tabular data just like that, we may not understand any potential pattern that may be existing. So let us put a scatter plot of this information. On the x-axis, I will put weight. On the y-axis, I will put length. And let me put the scale 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Similarly, here also I'll put 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I will put a scatter plot of each of the mouse that I measured and put there. So let me ink color. I will choose blue. Okay, so the first mouse is actually 2 and 3. It is falling somewhere here. Second mouse is 4 and 4. Let me take it like this, somewhere here. Then 3, 2, another mouse, little bit not very healthy mouse. It is not going very well. Okay, because when we see a population of mouse, we will see all types of mouse. Some healthy muscular mouse, they are growing very well. Some obese mouse, they are eating too much and growing in weight but not growing in uh, the length. And some mouse are typically not so healthy mouse, neither weight nor length they are growing. All mouse will come across. So that is the real data. Will have some pattern, and some outlier things also will be there. The outliers, we usually call it as noise. Keep that in mind. We'll talk about all these things, why model complexity becomes such a complex issue to deal with. So anyway, the fourth mouse is 5 and 6. Let me go and put here. Okay. Then the fifth mouse is 6 and 6, somewhere here. 6 and 6. Let me put somewhere here. Then the seventh mouse is 7 and 5. It is okay. Then the last mouse is actually 7 and 6, somewhere here. Okay, both of them are. So basically, we have plotted all 7 mouse in a scatter plot. Okay, so why we are doing? We want to see, is there any pattern in this? But then we want our computer to understand this data. We want to train using this data our computer, and then let the computer understand this pattern. And if it understands the pattern very well, then maybe it will predict very well. Okay, so let's go to another screen. What really modeling in a simple terms is that, so I have data, I want to give this data and make a model, and as I told you, our computer will figure out to understand this data, but I supply a set of algorithms. So the algorithms can be based on multiple computational ideas and models. Most of the algorithms we use mathematical mapping functions. Okay, like your linear regression, polynomial regression, logistic regression, all these actually are built based on the mathematical mapping functions. Okay, at times, to understand non-linearity in the data in a very natural way, sometimes mathematics cannot express the natural non-linearity typically exists in any data. That's where a very useful computer science model is actually called decision trees. Again, the computer science students in their curriculum, almost they study decision trees for a semester long time. Then the third most important problem that is solving these days, the deep learning problems, is our artificial neural networks. Okay. So any of these models we will use and help the computer to understand that mapping function that actually the input features and target variable seem to have. So typically mathematically, if we want to express it, we always use y hat, the predicted target variable, equal to a function of x. X is input feature. Okay, so here in our example of mouse, only one input feature, that is weight, but in a typical real projects that we will solve, these input features will be 100, x1, x2, x3, x4 to x100. Okay, uh, then anyway, let us today focus only on the mathematical function. Either of these things, you use a mathematical mapping function or a decision tree or artificial network. The goal of machine learning is that based on the input features x and y, actual y using which we are training, we have to let the computer figure out the real, the best mapping function that describes the underlying relationship between the target variable and the input features. If that is done in the most accurate way, then the predictive accuracy of your model is good. So either a mathematical mapping function or a decision tree or an artificial neural network. The aim is that when I use a particular data consisting of input features and a target variable, based on what I use, the model should figure out of many possible mapping functions, the best function that describes the relationship, the underlying relationship between my input features and target variable. Why the true underlying relationship is needed? Because any data I have, lot of trends are available in the data, but any typical real data will have lot of noise. Okay, like when we collect 100 mouse, there will be a lot of non-healthy mouse also in there. Basically, from a common sense point of view, what we know, if a mouse grows healthily, it eats and then it increases its weight. As it grows in weight, it also grows in length for a some time. After some time, if it keeps on eating, it will not grow in length, but it will grow in height. So basically, if you go back here and look at our, maybe based on common sense, if we let's say this is my green line, I'll use the, based on common sense, what happens, the basic trend is that it will go something like that. This is my, based on my common understanding of biology of mouse, this is my true underlying relationship. Now my computer also should be able to find that using any of these three techniques, by applying mathematical mapping functions or decision trees or artificial neural networks. So let us talk about mathematical mapping function at this moment. So we, to understand this problem, we help our computer with an algorithm, that is what we call linear regression algorithm. Okay, so basically linear regression algorithms we studied in our school time. If I have a particular data, if I want to fit a straight line, the best fit straight line uh, with respect to the data, we use a typical mapping function y equal to mx plus c. So we are just using our high school maths only. Basically, what is this? M is the slope of the line and C is the, we'll call y-intercept. Whenever x equal to 0, if a line cuts the y-axis, this is called y-intercept when x equal to 0. And the slope of the line actually describes the unit increment of x, how much increment y is doing. Again, this can be negative, positive, but this is the way we express straight lines through some data. So let us say we are using similar linear regression algorithm using this mathematical mapping function to understand our data. So typically what happens, our algorithm will use the same equation, but terminology wise we'll keep on using this beta 0 plus beta 1 x. This is called actually y hat. Y hat is nothing but predicted variable, predicted y. Okay, it's not actual y, it's predicted y. If you go back here, the length is y is here, is actual y. So it will also calculate this y hat, that is basically predicted y for that weight. So far I think it is clear. Please feel free to ask questions. I'm just, again, we'll do all this properly. Before I want to take you through that case study, I want a little bit of a clear understanding in your minds. That's why I'm doing this. So y hat here is predicted y. Beta 0 is nothing but our c, that is y-intercept. Beta 1 is our slope for a simple linear regression. So basically, when we use a linear regression algorithm and help our computer to learn this data, so what it does is that it looks at that data, calculates a lot of statistics. We can also manually calculate standard deviation, variance. Then it calculates finally and arrives at multiple lines through this data can happen. But the problem with linear regression is that it will only have a flexibility to understand the data using straight slanted lines. It cannot understand curvy relationships. It can only understand the data and represent it as straight lines. So what this algorithm will do, it will read the input features and also the actual voice, and based on whatever it reads, it does a little bit of calculations, and basically there will be a line, a point in this data, that is what we call a mean point, mean of x and mean of y, average of x and average of y. That is where it will actually just my ink color I will change. So this is the point, is a mean point for both x and y. So any regression line for this data always goes through this point. So to understand this data, many slanted lines can be possible. There can be a slanted line like this, a slanted line like this. Again, it is going via this, a slanted line like this, or a slanted line like this, or this horizontal line like this. Anything can represent this data. But how our algorithm finds out the best line that actually represents this data in the way, then all algorithms follow what we call a cost function. Okay, we'll come to this, all these things much more clearly, I'll explain. But typically the linear regression algorithms, they follow what we call sum of squared errors. Okay, so out of thousands and thousands of lines that are possible to put in the space of our training data, one line where the sum of squared errors is actually minimum. So the sum of squared errors function is called cost function. Every algorithm using any mathematical mapping function, simple to very complex, will be represented by one cost function, and the algorithm's goal will be for a given data to figure out the best model for which the cost function is minimum. The sum of squared error is nothing but, so for every actual y, my line I made, and from there I'll calculate also for everything a predicted one, and whatever error is there between my best line or whatever line I have put, and from using that again I will predict, and then I calculate the difference between them and square it, and again this is I equal to 1 to n for all observations. So this cost function has to be minimized. Wherever that minimum, that will stop there, and it will tell for your data, based on the model you wanted me to build using this algorithm, I am coming up with a solution, and this is my solution. So let us say I will again choose another color out of all the possible things. Okay, let me choose purple. So there is a line, this is my purple line, is my model, okay, which computer has recommended. Okay, so hope you're clear. So there are a lot of lines possible, but for this purple line, the sum of squared errors for this data is the minimum. So it has stopped there, and it has told, hey, this is your model. Okay, so basically what it would have done while training the data, it has figured out many lines, and the whatever, let's say first line it has created, and it calculated y hat, it was 4. So 3 minus 4 and squared, and like that it has calculated sum of that, all sums it has calculated for thousands of lines starting from the mean line, and turned it uh, counterclockwise, anti-clockwise, and figured out, and finally arrived at a particular this purple line, where if I calculate the sum of squared distances or sum of squared errors, it is the minimum. That is where it stopped. Okay, so that is how computers work. Now the problem with this mapping function is that no matter whatever is your data, this mapping function will help you to understand the data using slanted lines, straight lines. It doesn't understand any curvy relationship in the data. So let us say I want to give it more flexibility by choosing a different linear regression model, but with a polynomial terms for my input feature. So I am giving beta 0 plus beta 1 x plus beta 2 x square. So as you add, so basically what you are doing here is that you are increasing the number of features. Now input feature x is there, x square is there, y is your actual predicted variable, and this is the calculated predicted variable. So now your table not having one column as feature, it is having two columns as feature. Then your computer will figure out for the best curvy line what are the beta 1, beta 2, beta 3. So three coefficients will be calculated and given to you for the best line. If you want to give more flexibility, then you can increase your polynomial terms beta 2 x square plus beta 3 x cube. Then it understands more curvy relationship in your data. So basically, by changing your mathematical mapping function from a simple linear regression to a polynomial linear regression, you can keep on increasing this. Let's say you want to give a lot of flexibility, then you can go on beta 0 plus beta 1 x plus beta 2 x square plus go on beta 10 x to the power of 10. Then you are giving a lot of flexibility using your mathematical mapping function. Then it will learn the data and it will understand all the curves that may be existing. Some things unnecessarily also it will learn using both signal and noise. And then maybe it may create a model if you use y hat equal to beta 0 plus beta 1 x plus beta 2 x square, go on and on till, let's say, uh, you are using up to x to the power of 10 terms. Then this yellow line may be your model, like that. This will be the purple line for your simple linear regression, y hat equal to beta 0 plus beta 1 x. Now the yellow line, yellow model, computer figured out for this data. So using, because you have given a lot of flexibility to the computer to learn everything in the data. Okay. Now what you do using these models, you will go and for 6 what is my prediction based on the linear regression model. Then I have to go up to here. This is my 6 cuts here. This I have to put it here. So it is telling something like 5. And if I look at from the point of view of 6, or here it will be very accurate for 6 because already it is there. But let's say there is a 6.5 here, then it will give some data different than the line here in the purple line. So using these models, we'll start predicting these new unseen values. So now, in your opinion, what is the problem with the slanted line? Because as I told, this green line, I'm writing it on again on the yellow marker. This is actually, through common sense, we know this is the relationship. The slanted line is actually cutting across the mean data and going like this, and this yellow is going all the ways. So which model is best here? What do you say? Which will have better predictive accuracy? Are you able to hear me?
Yes, Madhu, we are able to hear you.
Okay. So my question is, what do you think is the best model? This very curvy thing which we got through 10th order polynomial regression, or
Yeah, polynomial regression.
we think like that. Okay, but the problem is that in this data there is a signal as well as there is a lot of noise. Okay, as you give lot of flexibility to this algorithm, then it will capture noise along with signal. Because it captures noise with signal, its predictive accuracy it is very good for the data using which you trained, but it will be very inaccurate for the new unseen data, because it has picked not only signal, but it is also picked noise. And problem with the first one is that no matter how much data you give, it will not understand the curvy relationship. Especially our common sense tells that beyond a particular weight, mouse will not grow in length, it will plateau there. Okay, so it will curve and then stay constant, so that it will not capture. But so it is basically, it is not able to understand the signal in a proper way. So maybe for this data, between these two extremes, simple linear regression to a 10th order polynomial, maybe a second order polynomial can capture that relationship better, the one we have put it as a common sense thing. So what we are telling is that when we build models, if we don't give them enough flexibility, we create a problem. Similarly, when we give lot of flexibility using our algorithms to learn data, we have a problem where they pick up noise and model accuracies, predictive accuracies will fall down. That is the point really we are talking, and that is what is this concept called model complexity. So we should not fall in
Madhu, sorry to
any of this.
interrupt you.
Yeah.
Madhu, sorry to interrupt you. Based on the data, how can we like notice that whether the data is a good data or noise data? So ideally, we will be getting numerous data, right? So among that, how can we come to a notice that it's falling under noise? Based on the is it based on the polynomial curve, or else like any
No.
outlier treatment we are doing?
So basically, that is a very important, good question, because that is the real problem. Whenever we get data, real data from real
Yeah.
population, it will have noise. Okay. Now, again, statistically, like you mentioned, outlier is the word used. Okay. Now, at the step of data cleaning, we do lot of analysis of data, visualize the data using many statistical descriptive analytics, as well as using a lot of graphs and charts to understand what you call this outlier analysis. Then we will pinpoint what are the outliers, potential outliers in the data. And then after talking to business people, after doing a proper conversation, we will, if we think that keeping these outliers in the data, it will lead in a wrong way to our model, then we will try to remove the data, clean the data. Or some occasions, you and your team may decide that no, this is an outlier, but based on our study, actually we want to really understand the behavior of the outliers also. Then you may keep it. It is one way or other way it will happen. But yes, uh, uh, one way to understand is that you have to do a lot of exploratory analysis of data, visualize your data, talk to people, understand the domain, and then do a very good outlier analysis, and then make a decision to either keep the data or remove the data. In spite of that, there will be noise. Okay, so that is the real problem. That is the why model complexity is so important. So typically in machine learning, people tell actually model complexity as the big boss. Okay, hope you are able to see my screen. I'm writing it in yellow. So what is big boss? When we play computer games, okay, we play against a villain usually. Then whenever we play, in the first 5 minutes, one villain will come. Like in our movies also, in a thriller movie, hero starts and then in 10 minutes, one villain will come. Then we think that this is the villain in the movie. But 2-3 minutes later into the movie, we'll figure out, no, this fellow is not a villain. He's only a chimcha of the main villain. Then another 30 minutes into the movie, another villain will come. Again, we think this is the big villain, but no. So finally, just maybe around interval and immediately after interval, we actually see this big boss. Big boss is actually big villain. So what is the real big boss of machine learning? This model complexity is the big boss. It is a real villain, which will, you as a machine learning developer, engineer, project manager, you are always fighting against this big boss. Okay. So anytime you fight against a big villain, okay, you have to have a lot of tactics. Okay. So when we do these projects, that is why I told this is the heart of machine learning. So you have to understand, as you are building projects on a continuous basis, you are applying some tactics to fight against this big boss. And this big boss for machine learning is model complexity. It is not an easy thing. That is why it is the most important concept. While doing project, lot of clarity you will get. Who asked the question? I want to know the name.
Sir, this is Jogaret.
Jogaret. So you will understand all these things. That is our goal. Right now, we are only talking about this model complexity from a very conceptual point, but that is the game of machine learning. If one game only we are playing, that is actually fighting against this issue called model complexity, and model complexity is the biggest villain of machine learning. Okay. So with this background, let us go back and look at, I wanted to talk about a real case study which happened actually. We want to see that how scientists gone wrong with building a particular model which caused a major disaster in human history. And that is why, again, maybe soon after this COVID is over or little getting over, definitely there will be a lot of critical discussions will happen on some of the models that have been created to predict the number of deaths, predict the growth of the COVID, and a lot of discussions will happen on that also. But this is also one case study I have. Again, this is available, University of Berkeley. They have put this to explain model complexity on the web. Just I picked it from there only. I have not created anything. So basically, model complexity is one of the most, if not the most important concepts in applied machine learning, and that is what we are really learning. So the case study I wanted to really talk to you is actually Fukushima power plant disaster. So this happened somewhere in 2011, February, March kind of time frame in Japan. There was a massive earthquake. It recorded 9 on Richter scale, which very unusually that kind of earthquakes happen. And immediately after that, there was a spectacular tsunami. All of us have watched it on the screens. So when that happened, actually Japan is prone to earthquakes, it's prone to tsunamis. So they have very good early warning systems and control systems to stop a lot of things. So this Fukushima power plant immediately was switched off. The fission reactors have been immediately turned off, which was to happen, and it happened. That's good. But what happened is that tsunami water entered the power plant. Typically, though fission reactors are stopped, they have to be cooled off. And to cool off, there are a lot of pumps through which water flows and it cools off that reactor. And to really operationalize those pumps, there are some generators which require power. But because of this tsunami warning and water entering, the power to the generators was switched off. Because of that, there was no cooling that happened to these fission reactors, though they were switched off by the time, but they were very hot inside. So a nuclear melt happened, and some contamination happened in that area. And it is recently, if you look at a major nuclear disaster, Fukushima disaster is considered to be one of the most catastrophic disaster. It happened that way. So Japanese scientists are very good. though they actually design and build the most reliable nuclear power plants. Typically, whenever somebody in those kind of earthquake prone countries, people are designing nuclear power plants, they will use some kind of prediction model. So how likely a particular uh, Richter scale, on Richter scale, particular strength earthquake, what is the, how many years once it is happening? They want to do a little bit of the prediction, and based on their learning from the data, they will design, because I can spend billions and billions of dollars and build a nuclear power plant which can withstand a Richter scale 9.5, but then it will cost me some $500 billion, let's say. I'm exaggerating. Okay, but what is the likelihood of occurrence of a 9.5 on Richter scale earthquake? Maybe once in 500 years. So should I spend all that money? So why don't I build a power plant that can withstand 8 instead of 9.5? So that kind of cost benefit analysis engineers and scientists do, because everything is costly. So basically people will be very careful. So basically the engineers of the nuclear power plant, actually there is a useful technique also. There are two scientists who are very famous actually. One is Richter, on whose name the Richter scale is actually named, and there is another German scientist called Gutenberg. So there is a Gutenberg Richter rule for predicting earthquakes of particular intensity. There is a rule they have actually theorized long back. Okay, so basically what they tell is that we can predict the likelihood of occurrence of a particular strength magnitude earthquake, and they theorize that the relationship actually between the magnitude of an earthquake and the logarithm of probability that it happens is linear. What is this logarithm of probability means? Like every day there are a lot of low intensity earthquakes take place. Okay, so using that frequency of low occurrences, low intensity earthquakes, which happen every day many times, and for the last 400 years geologists have been recording, so there is a huge data of a particular earthquake intensity and how periodically it is happening. So that kind of tables are there, and the relationship between the table things is linear. That is what Gutenberg and Richter generally theorized, and it follows that. Okay, so basically the engineers of the nuclear power plant used earthquake data from the past 400 years to train a regression model. Actually, when they built model, it looked something like this. Basically, what is happening here is that if you look at the dark diamonds there, that is basically your scatter plot. So on x-axis you have earthquake magnitude, okay, and on the y-axis you have logarithmically scaled uh, frequency of occurrence of such a strength earthquake. That is what is the data. So there is a lot of data available for the past 400 years. So y-axis is a put on logarithmic scale, x-axis is your strength. Look at it. So they have used, like what we did for the rats now, they have used it, and there is a linear relationship. That is what established by these two scientists. So they used a particular mapping function, and this line here, let me put my pen. Okay, so this dark line, whatever you are seeing here, this is your model. Okay, so basically underneath these diamonds, there is a dark line that is going like this. Okay, so basically if you look at this line, they've used a particular mapping function, and they can use this model to predict. Now let's say somebody asks a question, hey, if what is the likelihood from this model of occurrence of a 9 on Richter scale, then we can go back and put somewhere here, and on the logarithmic scale, whatever it is that we can figure out. Okay, So basically, they use this model. If you look at this model, it is not a straight line. Somewhere here, 7.3 or something, it is taking a curvy route. It's coming up till here, some straight, but here it taken a curve, and then it went on straight again to predict higher frequency thing. So they use this model, and because they wanted to design this power plant for a particular, so they asked a question: 9 on Richter scale, how likely or how many years once it happens? Then, according to this model built by the scientists, it predicted one earthquake of at least magnitude 9 about every 13,000 years, because it's a logarithmic scale. If you take to the y-axis, it is 13,000 years once actually an earthquake of magnitude 9 to occur, which is really long time. So there is no point right now designing a power plant by spending a lot of money for some event that will happen only once in 13,000 years. But how did they come to that conclusion? Using this model. Okay, this model, it is very closely fitting to the data. It appears like very good that it is, but this data might have noise also. Okay, but it fits very well with the training data of 400 years. Then, based on that, they designed this plant. So they thought that never it will happen, but actually, in fact, what they decided that anyway, let us not do for 9, let us build for some 8.5, which is some 300 years once it will occur. So let us spend money and build for this kind of earthquake. Let us forget about this 9 kind of earthquake. Okay, that is how they have done. But what happened? A 9 earthquake happened, and nuclear melt happened. Lot of problems have happened in Japan. So it was a disaster for them. It was led by a model which wrongly directed them. But if the scientists would have used the Gutenberg and Richter rule in a proper way and agreed that, okay, no matter what, the relationship is linear, and if they could have built a model, a good model, or in this case, after the post facto, we can always tell, if the engineers had used the correct linear model using the right level of mapping function, not making it too flexible, making it more complex, if they would have kept the flexibility to the only limits of what naturally it is occurring, then this actually is a, it doesn't capture curves in the data. So basically in the previous one, here the curvy thing it has captured and it kind of tilted a little bit. Whereas if they've used less flexible mapping model, mapping function, it would have followed this straight line. Okay, so it is cutting here. So now if you ask a question, hey, what is the likelihood of a 9 thing to occur, and we take it to y-axis something, it will be 300 years. Okay, so with this model, the correct model would have predicted one earthquake of at least magnitude 9 just about every 300 years. Okay, then it would have driven the scientists in the right direction. They would have taken some precautions that typically occur when a Richter scale 9 kind of thing happens. So basically what happened in the first model, they have given more flexibility to the mapping function to understand the data, or in other words, they made it more complex. And because they made it more complex, actually the model understood data and also understood the noise. That's what is happening around 7.3, where some noise of data is there. It captured that, and because it captured that kind of models, we usually refer to it as overfitted models. Okay, whereas in this model, they have not given too much flexibility to the model to understand the curvy things, because anyway the rule itself says the x and y have a little bit of linear relationship, so they did not allow that flexibility, and the model is only representing the data using a slanted straight line. No curves are being kind of taken into account. So and because of that, it is able to give better prediction. So this is what is a problem we usually face. So just to cover whatever this Fukushima power plant disaster, so the actual model predicted one earthquake of at least magnitude 9 about every 13,000 years, because we have given too much flexibility to understand the data and made it a overfitted model, while the correct model would have predicted one earthquake of at least magnitude 9 just about every 300 years. And because of this, the Fukushima nuclear power plant was built only to withstand an earthquake of magnitude 8.6. That is the design parameter they considered. The 2011 earthquake that devastated the plant was of magnitude 9, for which it was not designed. Actually 9 was about 2.5 times stronger than a magnitude of 8.6 earthquake. So that is what is the problem while we are building models. Always in the data there is a true underlying relationship, and because it is real data, in any real environment there is a randomness in the data. That randomness we refer to it as noise. Now as an engineer, you have to actually build a model that is not too complex nor not too simple. So you have to do a very careful balancing act and keep on fighting against this issue of model complexity and build a model that really is useful for humanity. That is what is the real issue of model complexity. So we have some questions now, you answer. With that, I think understanding will be complete. Then anyway, I will define few terminology for you in today's lesson. uh, Overfitting, underfitting, then bias variance, very quickly in a simple terms. So it will take maybe another 20 minutes. We will complete this today. Okay, so answer questions now. The first one says that there may be some underlying relationship between the input features and target variable. True or false?
True.
True. Any data, at least some features will have some relationship with the target variable, and that is what we want to really understand. Okay, that is what we want our model to kind of capture and to create a good model. Okay, it's a true. The purpose of machine learning is to estimate that true underlying relationship based on the data set that you have. Agree or not?
Agree. True.
Agree. True. Okay. The third point is there will be some randomness. We are calling it as noise in any data, and your model should capture it as well. True or false?
True.
True.
There will be some randomness in the data, in every data, and your model should capture that it as well. That is what happened in the model created by Japanese scientists. There is around 7.3 to 8. The data has a lot of randomness, and that is where the model captured the curvy thing and then it directed in a wrong way. So should a good model capture noise also? True or false?
True.
So good models
False.
should capture
False.
noise. Good models should not capture noise. If they capture noise, disasters will take place. That is what your Fukushima experience is saying. Okay, so that is basically a false statement. Those who are telling true, please think once more. I'll read it for you. There will be some randomness in any data. That is noise. Like in our mouse example also, there are some mouse of bad health. Okay, they are not growing in weight, and also so they are little bit outliers. So if you build understanding about the trend, then you will capture that also. But a good model should avoid that. Good model has to understand a simple pattern that actually, yes, generally up till some weight, height will increase or length will increase. Beyond a particular weight, uh, the length will become kind of flattened. Okay, that is the common sense says. So any model which takes that kind of understanding, that is a good model. If it is kind of driven by all the noisy things, very obese mouse with some 2 centimeters in length but 50 grams, that is a very obese mouse, some problem is there. Those are all outliers, noisy mouse. So you have to avoid that. So I'll read it again for those people again. There will be some randomness in the data. Randomness, I'm calling it as noise, and your model should capture it as well. Actually, should not capture. That is the right answer, true answer. If it is should capture, it is a false. Hope you got it. Okay, let me read the fourth one. Good machine learning model captures the true underlying relationship signal between input features and target variable. True or false?
True.
True.
So a good model will capture only the true underlying relationship and ignores noise. Okay. Fifth one, a model that is not flexible enough to learn the signal. So too simple basically. It is not able to understand the true underlying relationship, as well as a model that learns noise instead of true underlying relationship. Both of them are considered good models. True or false?
False. False.
False.
So
False.
one is not understanding the signal itself, one side, that is too simple. It is not at all, we are not at all giving flexibility. And on the other side of the spectrum, it is understanding randomness also and making it very complex. It is having too much flexibility to understand the data. Then both of these models are not good models. The first one, which is not flexible to learn the signal, we call it as underfitted model, is not good. And the second one is actually understanding noise instead of the true underlying relationship, then it is called overfitted model. So both underfitted and overfitted are not good. Okay.
Good.
So
False.
yeah. Okay, false. So model complexity is one of the most important concepts of practical machine learning, and we continuously fight against this villain as we build projects. There are a lot of tactics, and all those tactics we learn as we build projects. So quickly, again, recap on some of the concepts. We defined machine learning as the practice of teaching computers how to learn patterns from data, often for making decisions or predictions. So when we teach machines using data, using our model training process, the output that will be generated is a model. And what is a model? It is a simplified representation of the real world that still accurately captures a desired relationship. It is a simplified, it is not a over complex representation of the relationship. If it is over complex, it doesn't solve any problem. It is too simple, it will not solve the problem. It has to truly represent the real nature of the world, real nature of the data. That is important. And again, going back to our example of machine learning definition, so we talked about the story of the kid. The kid has actually created a very simple model. The kid has not created a very over complex representation of what she got trained or experienced. She put in her mind, red and bright means pain. Okay, she doesn't understand thermodynamics. She doesn't understand nerve endings. She doesn't know how brain works. She doesn't understand how pain is caused. Only based on experience, she understood anything red and bright may be pain, and that is how she protected herself with a new unseen data. So it's basically a good model is a simplified representation of the real world. And for a model to be useful, it must accurately capture a useful relationship. Okay. And machine learning builds models by learning the real patterns from data, and model is an output of the machine learning process. That is what we have talked so far. So as I told you in my whatever thing, so typically representing whatever the relationship between my predicted target variable as a function of my input features. So x is my input feature. Anyway, in our simple example, it is only 1x, but real projects, there will be at least 100 x's and one y that you have to predict. Out of these 100 features, some will have more different. So it's a complex problem. What we have taken is the rat is a very simple thing, but when we do our real projects in this course, we'll see that how do we take care of many things. So x basically is the input feature, y hat is the predicted target variable, and the real thing we are doing is that we are actually finding out the right function, mapping function between x and y hat. So in our linear regression, as I told you, many different slanted lines are possible with different beta 0 and beta 1 numbers, but one line where it has the minimized cost function, that's what we call squared residual errors or squared errors. Sum of squared errors is the minimum, and typically many other mapping functions, if you use partial differential equations in particular thing, then a different cost function will be applied, but there is always a cost function that helps algorithms to understand data and arrive at some the best curve or best line or best section of whatever data there. So actually what you are really doing, the purpose of machine learning is to estimate this mapping function, correct mapping function based on the data set that you have. You should not make it very complex, you should not make very thick. So key questions you have to ask when you build the models: which type of algorithm should I use to build the model? Okay, that is a very important question. We'll work on that. Then which algorithm settings should I tune so that all these model complexity issues I am fighting cleverly? Then how many features should I include? Like in a table, there are 200 columns. X is not one column, but X is X1 to X250. So sometimes more features means more dimensions to the problem. And as the dimensions increase, model complexity increases. So how do we reduce it? What is the strategy? What is the cleverness that we have to apply? We'll talk about all these things. So model complexity is a critical issue, and you have to do a very good balancing act. So the way we define model complexity is models inherent flexibility to represent complex relationships between input features and target variable. It is inherent flexibility that you are giving to train. So if you give too much flexibility, then you are underfitting the model. If you are giving too less flexibility, not too much, if you are giving too less flexibility, then you are designing to fail by producing underfit model. It will not understand even signal. If you are providing too much flexibility, then you are making it very complex and you are making it a overfitted model, and then it picks noise also and makes the model very inaccurate for a new unseen data. So we have to guard against both the things. So model complexity, again, to especially those who want to go interviews and all, sometimes you have to understand these definitions. So I'll repeat again: model complexity is models inherent flexibility to represent complex relationships between input features and target variable. Okay, so this model complexity issue can be understood through many prisms. One prism is actually electronics prism, that is signal versus noise prism. So signal is basically the true underlying relationship between input features and target variable. Okay, and noise is the randomness. Okay, like your mouse, obese mouse, or bad health mouse, whatever is that. Okay, so a good model basically captures signal and avoids noise. Okay, that is what we are telling. One practical challenge in real world machine learning problems is dealing with noise. How do we actually avoid learning noise? Therefore, one way to judge models is by their ability to separate the signal from that noise. So a good model separates noise from the signal. Not so good model will not be able to separate noise from signal, and they get overfitted and they will be bad models. Okay, so other definition also I've been using. So let me define. So overfitting versus underfitting. So using that signal noise only we do that. Okay. So overfitting occurs when the model learns the noise instead of the signal. Then overfitting occurs, and this tends to happen when the model is too complex. So for a mouse problem, weight and height, you use a 10th order polynomial regression mapping function, then you are by design making it very flexible to understand the data, so it becomes overfitted. Then underfitting is occurs when the model is not at all flexible enough to learn the signal, and this tends to happen when the model is too simple. So I put y hat equal to y average. So horizontal line across my y-axis I put, and that is the model. Then it is too simple. It doesn't understand any relationship between input features and target variable. So more questions now for you. Okay. So underfitting is when we train a predictive model that hugs the training data too closely. True or false?
False.
False. If it is hugging too closely, like our Fukushima thing, means it has become already overfit. It has taken a curvy route at the place where noise is there. Okay. So it is a false statement. Good. The second point is you have state-of-the-art algorithms, the fastest computers, and the most recent GPUs. GPUs are graphical processing units. But if your model overfits or underfits to the training data, its predictive powers are going to be terrible, no matter how much money or technology you throw at it. True or false? Is it true?
True.
It is not about technology. It is not about a smart algorithm. It's not about speed at which you are able to compute. All these are useless if your model you have actually either created as an overfit or underfit. So it is a true statement. Then the third statement, I'll read it for you. When a model ignores important features of our data set and is not complex enough to capture important features, that is called underfitting. True or false?
True.
True. So it is not complex enough, and it is not even understanding signal. It is an underfitted model. So some more questions. So I have pictorial representation of some models for this scatter plot, this data. You are able to see this and create a pattern there visually, though in most of the cases with multiple features, anyway, you will not be able to also visualize. But here only there is X and Y. So which is the first model is what? Is it underfitted, good fit,
Underfit.
or overfitted?
Good.
It
Good
is
fit.
underfitted. Which one? First one.
Underfit.
Underfitted.
It is underfit. By seeing, we can see it is taking a U kind of shape. As time is increasing, the values are falling up to one value, and beyond that value again they are going upwards. That is what is the basic trend. So good model has to capture that relationship, whereas this is a simple linear relationship. It is a underfitted. The second one is a good fit or overfitted.
Overfit.
In this whatever pattern, there is lot of noise also may be there, so it has remembered every data point there. It is crisscrossing through every point, and it is actually capturing noise also. So maybe they have given too much flexibility by giving a very 100th order polynomial regression equation, and it has captured, or it has started remembering all values in the table. So it is a overfitted model. Third one is
Good fit.
good fit. So hope in your minds it is clear about this model complexity. Again, even if it's not very clear, don't worry. This is what we will keep on talking, because this is the biggest villain in the ML game. Okay, so the last section, again the same overfitting, underfitting, signal versus noise, some terminology also from an interview point of view, these are all important because in interviews typically they ask, and these are a little bit, we can go into a lot of depth mathematically and explain, but that is not our goal. And we deliberately, we are not doing it, but I will keep you with some basic ideas in your mind. Okay, the same thing can be explained using this terms bias and variance. So let me explain that. So the bias variance trade-off has simple practical implications around model complexity. So though this is another way of explaining model complexity and basically the concept of overfitting and underfitting. Especially we classify a set of algorithms as some algorithms are high bias, low variance algorithms. Some algorithms are high variance, low bias algorithms. So we want to understand so that we choose the right kind of algorithms for right kind of problem. That is why understanding this bias variance trade-off is also important. This is our last section. It may take another 5 minutes. Just bear with me. So a set of algorithms, we call them high bias, low variance algorithms. So basically bias occurs when an algorithm has limited flexibility, like you are using y equal to beta 0 plus beta 1x for a problem where it is taking some hyperbolic kind of curve. Then basically you are using a high bias, low variance algorithm because this slant, this y hat equal to beta 0 plus beta 1x, no matter how much data you give it, it will always represent a slanted straight line. It will never understand the concept of curves, that curvy relationship that may be existing. So bias occurs when an algorithm has a limited flexibility to learn the true signal from a data set. Maybe that's what a high bias algorithms are basically cause underfitting problem. Okay, so to understand high bias low variance, so if you have a dot board like this and you are throwing and you have to hit this center, but if you are using high bias low variance algorithms, all your 5 dots that you are throwing, they will be very consistent, they will fall in one place, but they will not be accurate, they will not hit the center, but all of them will go and fall in one place. So they are consistent. High bias low variance algorithms, they train models, and the models produced are consistent in predictions but inaccurate on average. So they give consistent outputs, but generally they are inaccurate. That is the problem with high bias low variance algorithms. Means you are talking about basically underfitted models you are creating using these algorithms. On the other side, you can use high variance low bias algorithms. So now you have used, to understand the weight and length problem of the mouse, you have used a 15th order polynomial regression model. So y hat equal to beta 0 plus beta 1 x plus beta 2 x square plus beta 3 x cube beta 15 x to the power of 15 kind of thing. Then you have given it a lot of flexibility. It is very sensitive model to capture everything and understand the relationship in a total flexible manner. So variance refers to algorithms sensitivity to specific sets of training data. Okay, they are very sensitive. So these kind of models, if you look at it, they are accurate for some data points, very accurate, but they are very inconsistent. Okay, especially these high variance low bias or overfitted models, they are highly accurate for the training set data, which whatever training you have given, for that data it is accurate, but you show some new data, then it will be totally inaccurate. So basically high variance low bias algorithms, they train models that are accurate on average but very inconsistent. So both are problems. So high variance low bias models are algorithms that create these models, they create overfitting problem. High bias low variance algorithms, they create underfitted models. So you have to strike a balance between that. That is what we call a proper trade-off. So like one of you asked that question, how do we solve this? There are a lot of tactics to solve as we do the projects. You have to separate training and tests and conduct a lot of while you are building models, you test the models, you tune the models. to understand this overfitting kind of problem. Then you have to try appropriate algorithms. Then you have to tune with right model parameters. Then you have to, every algorithm has hyper parameters, so you have to tune using those things. Then you have to establish right performance metrics for the accuracies of the models. And then there is something called cross validation. All these are, again, there are some more things that will come to learn, that is regularization, bagging, boosting. These are all techniques and tactics to systematically fight against the model complexity issue, and we'll apply all of them as we do the project. So now I have questions on our bias variance thing. You have to answer. So bias refers to algorithms sensitivity to specific training data. Yes or no?
False.
False. Actually, variance refers to algorithms sensitivity. You are giving it too much sensitivity by having high degree of variance. High bias, low variance algorithms train models that are consistent but inaccurate on average. True or false?
True.
These are underfitted models. It is true. Okay. The third one is a proper ML workflow with separate training and test sets, systematic cross validation, appropriate tuning of model parameters and hyperparameters finds optimal balance between bias and variance. True or false?
True.
True. These are the tactics. Anyway, right now you may not understand this terminology, but never mind, you will get them with a lot of clarity as we do the work. So don't worry, but it is true. The fourth statement is variance occurs when an algorithm has limited flexibility to learn the true signal from the data set. True or false?
False.
False.
False. Variance is actually causes too much sensitivity. It actually doesn't cause limited flexibility. High bias actually causes limited flexibility. So basically, high bias, low variance is underfitting. High variance, low bias is over.
We lost you, mother. We are not hearing.
Now we can hear you, Madhu.
Okay, actually, I think I lost you for a while. I'm reading it again. My mic, I don't know, muted somehow. So what I'm telling is that the risk in following ML models is they could be based on false assumptions and skewed by noise and outliers that could lead to making bad predictions. True or false? True or false?
True, mother.
Actually, it is true. Okay. Bias is how far are the predicted values from the actual values. If the average predicted values are far off from the actual values, then the bias is high. True or false?
True.
Yeah, they're consistently inaccurate. Okay. Models with high bias tend to overfit the training data, while those with high variance tend to underfit. True or false?
False.
False. Yeah, it is the opposite actually. Models with high bias tend to underfit, and models with high variance tend to overfit. That is the true answer. So it's false. You are right. Fourth statement: high variance causes overfitting. That implies that algorithm models random noise present in the training data. True or false?
True.
True. So basically, high variance causes overfitting. Overfitting means capturing noise. Okay, random noise. So the last question today, I took a little bit more of your time. Sorry for that. because I wanted to close it logically and go to Python from tomorrow, next day, Friday. So you have to fill in these blanks. There are 4 questions, 6 items you have to fill. Dash occurs when machine learning algorithm captures the dash of the data. Again, it is a little bit, I could have used little differently, but okay. Based on the data available there, it can be anyway. Underfitting occurs when machine learning algorithm doesn't capture the signal, but that is not there. So it is overfitting occurs when a machine learning algorithm
Nice.
captures dash of the data, noise of the data.
Nice.
Second question is overfitting occurs if the model or algorithm shows dash and dash. So
Low
high variance
bias.
and low bias. Underfitting occurs when a machine learning algorithm cannot capture the dash of the data, cannot capture the underlying trend of the data. Okay. And fourth one is dash occurs if the algorithm shows low variance and high bias. Anyway, only one is there, but underfitting. So today we talked about model complexity. So please reflect. So what we are telling is that we are actually taking data, and unfortunately any real data will be having some good data and some lot of outlier data, and a good model actually filters out that and builds a model that truly understands the underlying relationship between the input features and the target variable. If it is able to do that, the predictions that it makes will be much better. Either way, if it goes wrong, that it is not able to understand the true underlying relationship because I am using not giving good flexibility using my mapping functions, then it will underfit and it will be not good. And on the other side, if you give it too much flexibility by making it extremely complex to understand every aspect of the data and noise, then it will overfit and then also it will not work. That's what we told. And we also told it is the heart of machine learning, and another way also I used it is the big boss of machine learning. So against this big boss we have to fight, and we will learn all the tactics to fight against this villain and build good models. Again, this is a foundational course only. I will give you through some projects some tactics, but then you have to spend your own time, learn it more deeply, and as you want to grow and become a much more professional data scientist or machine learning engineer, you have to further learn. But till that time, learn, have fun, and sorry for taking a lot of time, but in case anyone has some questions, please ask.
Madhu, you said like you'll be sending the instruction for Python installation,
I
right?
sent it already.
Oh, okay.
Because I
I'll
actually,
check that.
whoever email IDs are there, I'm sending it. Every day's link as well as whatever this kind of things. Because as we do Python, I'll be keep on sending you more things, some data. Even when we do projects, also I'll be sending the data sets because you have to have them. So again, those who want to get that mail and not getting, maybe I don't have your email ID at the moment. So let me write it again here. And any of your friends are not receiving, help them. So if you write Madhumurthy Ronanki at gmail.com, my daughter is keeping all the data and every day she is sending to the distribution list. So please keep this Madhumurthy Ronanki at gmail.com. So or if you are, some of you have not received, please write to this email ID. By evening I'll take care of it. So Friday
Madhu,
we'll start with, yeah, go on.
for confirmation, we need to have the Anaconda installation when we have the next session, right?
Yes.
Okay, so also to make it to clear to all other participants also, I'm asking this question.
Yeah, absolutely, because that will be easy. Whatever 1 hour we'll spend, because I'll be copying and pasting my Jupyter screens onto PowerPoint. So you can see that and even type the code at the time of class itself. Otherwise, you have to spend 1 more hour to do that, and sometimes busy schedules, you will not get time to do that. So my recommendation is always, let us do it together as much as possible based on your convenience. I don't know how, what kind of system using which you are learning at the moment. If you have a laptop or a computer, you can put 2 screens together and do it.
Yeah, sure. Okay.
Yeah. Okay. So thanks so much for your time. So have a wonderful day. Learn, have fun.
Thank you, Madhu. Bye.
Thank you.
Bye-bye.
Thank you.